We are continuing our analysis on the RLC circuits. So here's an example of an RLC circuit. There's two different types that you're going to have. You're going to have the parallel. This is a parallel RLC circuit. And we talked a little bit last week about the series RLC circuit. And we'll go back to the series RLC circuit in a bit. But here is an example of a parallel RLC circuit. Okay, warning right now, there is going to be a little bit of math involved here because now we are no longer Physics C students. So get ready for that. So here's my circuit diagram. Okay, you can see that these are in parallel. And for a reason I'll tell you later on, the current in the capacitor is going in one direction. The current in the inductor is going to go in a different direction. And the current in a resistor is going to go down that way. So there's three different currents going on here, okay? What we're going to use is Kirchhoff's equation, but there are two Kirchhoff equations. There's a current loop equation, and then there's the voltage equation. What we're going to use is the current equation of Kirchhoff's loop rule, okay? So if this is how the current is being portrayed, what I could say is that this current plus this current plus this current plus this current has to equal 0. So we have the current through the capacitor plus the current through the inductor, L, plus the current through the resistor, and all of that is going to equal 0. Now, later, what we could do later on is make this question even more difficult by attaching a battery. But right now, there's no battery here. We just have a capacitor, inductor, resistor. So here's my current equation. Now, what I'm going to do is I'm going to rewrite this current equation in terms of voltages, okay? So let's talk about the current through a capacitor. Well, capacitor, we know that Q is equal to C times delta V. If I want current from here, I would have to divide both sides by T, or delta T. So we would have delta T here and delta T over here. And so what we end up right here is current I. This would be the current through the capacitor. And that's going to equal C times, and instead of delta V over delta T, I'm going to write it as dV over dt. So the first current, I'm going to rewrite as C times dV over dt. Okay? So I'm just replacing current of the capacitor with this term right here. Hopefully no problems there. Let's go on to the current of the inductor. Now, the current of the inductor, we have an equation for the voltage of an inductor. We'll write it as the voltage of the inductor is equal to negative L times di dt. And so if that's the equation for the voltage of an inductor, this one we should know. The voltage of an inductor is equal to this term right here. What we could do is solve for I, okay? So bring the dt to the other side. You could leave the negative sign, whatever you want. In this case, the negative sign is going to go away, so we'll get rid of that for now. So bring the dt to the other side, and we get di is going to equal 1 over L. I'm bringing it to this side. VL dt. And if I want to solve for di, I have to integrate both sides. So I get I of the inductor is going to equal 1 over L, the integral of the voltage of the inductor times dt. Okay? So hopefully you can see where I'm getting this from. And I'm going to get rid of that subscript when I plug it into here. So the voltage of the inductor is going to be given as 1 over L, the integral of the voltage multiplied by dt. So we have the voltage of the capacitor. We've solved for this. We've now solved for this. And what is the voltage of the resistor, or in terms of the resistance? Well, that's just Ohm's law, V equals IR. So if we solve for I, it's going to be V over R. And all of that is going to equal 0. So what letter? Let's see here. I'll use squigglies there. Okay, so we have that equation so far. So far, I'm hoping you could at least follow along here. Now, I don't want an integral sign here. So in order to get rid of this integral sign, I'm going to multiply this side and this side by d dt. So I'm going to multiply this entire part right here. So I'm going to multiply this side right here, which is this, by d dt, and I have to multiply 0 by d dt, which is just going to be 0. Okay, so when you take the derivative of all of this, so d dt of this will become the second derivative. You get c d squared v over dt squared. That's when you distribute the d dt into here. Plus, now when you distribute the d dt into here, the integral sign will go away along with the d dt term. So what we end up with when you multiply this by this is just going to be v over L. Okay? And then you multiply d dvt on that side. So when you take this d dt term and you distribute it here, it's going to be plus, we'll take the r out, and we'll have dv dt. And all of that is equal to 0. So we've got a second order differential equation here, but let's clean it up a little bit because I like to look at it a little bit nicer than that. And I usually don't like to have coefficients in my leading derivative term. So we'll divide out the c from everything and we'll put everything a little bit cleaner. So I'm just going to rewrite this as this. We get d squared v dt squared plus, I'm going to use this term first, so that's going to be r over c dv dt plus this term with the c divided out. So that'll be v over L times c. And all of that is going to equal 0. Now this is what we're after here. This is a second order differential equation. Okay? And how do you solve this second order differential equation? Well, what I do is I use what's in here. And then from that, I remember that I have a book called Differential Equations right here. Here we go. And so I look inside my lovely differential equations book. And over here, I go into the second order differential equations chapter, and I look up what the solution for this type of differential equation would be. And we're going to have to write a characteristic equation for it. So what we're going to do, this might be new to some of you who are watching it later on and haven't taken any differential equations. You might not know this, but this will be new for you, and I hope you learned something. If you have taken DiffEqs, then it shouldn't be too bad for you. So we're going to try to solve this differential equation here. When I say we try to solve the differential equation, look, we've got v, v, v. We want v as a function of time. So what we're going to do is we're going to take a guess at what we think the general solution could be. Now, it might not work out, but we're going to guess it and we're going to see what happens, okay? So the guess that we're going to make, the solution to this differential equation, the guess that we're going to make is this. We're going to say that the voltage as a function of time is going to be given by this equation right here. a, which is a constant, e to the power s times t. Okay? In the differential equation book, it uses like s and r or something like that. So whatever, it doesn't matter. So this is going to be our guess. The velocity as a function of time is equal to a e to the power st. I don't know what s is. I don't know what a is, but we'll worry about that later. So if we look at our differential equation, well, we've got that part written out, but we need to take the first derivative of it, and we also need to take the second derivative of it. So what I'll do is I'll do that right now. The first derivative, which we could write as v prime t, is going to equal, well, when you take the derivative of this, it's going to be a times s e to the power st. So that's the first derivative. Then the second derivative is going to be v double prime of t is going to equal a, and then you bring another s out, and that's going to become s squared e to the power st. All right? So those are my function, derivative, second derivative. And now what I can do with these is plug it back into this equation right here. So the first thing I need to do is plug in for d squared, or the second derivative. That's this term right here. So we get a s squared e to the power st. Next, we're going to add to it the r over c. So that's r divided by c. And then we have to multiply that by the first derivative. That's this term right here. So that's going to be a s e to the power st. And then finally, the last part is v over LC. So I'm going to do plus 1 over L times c. And I'm going to multiply this by the v term in the numerator, which is a e to the power st. And all of that has to equal 0. So when we set it all equal to 0, notice I'm just taking the guess that I had. I took the first and second derivative. I'm plugging it back into my differential equation. And this is actually how you solve a second order differential equation, if you didn't know that before. Well, this is at least one technique in solving it. So from here, some stuff happens, doesn't it? Well, all the a's can get canceled out. All the e to the power st's can get canceled out. And what we're left with is s squared, that's that, plus, what is this? R over c times s plus 1 over L times c. And this is all equal to 0. There's a name for this right here, what I've just left with right here. The name for this equation that doesn't have any more v's in there or anything like that, this is called the characteristic equation. Okay? So this equation right here is what we call in math and physics a characteristic equation. And it's going to tell us a lot of what we need to know. Now, if we wanted to solve for s, this is a quadratic equation, s squared, s, and no variable here. So if we solve for s, what we'll get is that s is going to equal negative, whoop, I'm going to run out of space here. Let's see, what am I going to do? I'll try to write tiny. So s will equal negative 1 over 2 times RC plus or minus the square root of we're going to get to that. This is the characteristic equation. We're gonna find the determinant right now. So the determinant is actually what we're going to be doing in just a second here. So just hold with me for one moment, just one moment. So over here we have 1 over 2 times RC squared minus, is it minus? Yeah, minus 1 over L times C. And this is the determinant that you're after here, the thing that you're talking about. This is technically the characteristic equation, but you can solve it, and then the determinant is the part of the characteristic equation that you want. So here we just solve for S. Now, I want you to think about this for a second here. A lot of things are going on here. First of all, there's a plus or minus. That means your differential equation actually has two solutions. Let me repeat that one more time. There's a plus or minus for S equals all of this. So if you do the plus version of it, you'll get one answer. If you do the minus version, you get a second answer. So there are two solutions to the differential equation, which means that this is actually wrong. Okay? This is going to be incorrect. The way we're going to write it, I'll tell you in just a second. Now, the second part of this equation that you can find interesting is what's inside the determinant, as Zoe, you're saying. So if this value, if this term right here is bigger than this term right here, well, you'll get two real solutions. But if this value right here is bigger than this value, you'll still get two solutions, but they're going to be imaginary because this is negative. And then the last situation would be when this value is equal to this value, in which case you would get a real solution because the square root of 0 is still 0, it's a number, which means that your two solutions are going to be exactly the same. Okay, you'll get identical solutions. So there are three different, hey Helen, you missed a lot, but we're going to review this again in just a second. So you have three different values here, okay? So what do I want to do? The first thing I'm going to do is I'm going to rewrite this a little bit because it's kind of difficult to keep writing all of this nonsense out again. So the way I'm going to do it is like this. If you don't mind, I'm going to erase some of this board right here. So hopefully we're good with. I markered myself. Hey, if you marker yourself, doesn't that mean you just marked yourself? You wouldn't say I markered myself. Anyways, because there's a plus or minus here, we have to rewrite my original value. The way I'm going to write it is like this. V as a function of t is actually going to equal a 1 e to the power s1 times t plus a 2 e to the power s2 times t. So that's how I should write my differential equation, or my solution to my differential equation is going to be v as a function of t is going to be that instead of this. Now, something else is I want to rewrite s over here, okay? Instead of s, I'm going to write it as s1, 2, because we have an s1 here and we have an s2 right there. And I'm going to write that like this. s1, 2 is going to equal negative alpha plus or minus the square root of alpha squared minus omega naught squared. So if you can see what I've done the substitution of, you would see that alpha is really just 1 over 2RC, and omega naught is going to equal 1 over the square root of L times C. There's a lot to digest here. Now, these two actually have names. This is called your natural frequency. So if you didn't have resistance here, the circuit, the current would oscillate back and forth with a natural frequency of 1 over square root of LC. And we actually derived this when we were talking about LC circuits. Over here, this is a very important term here. This is called our damping factor. And our damping factor will tell us if our circuit is going to be overdamped, underdamped, or what we call critically damped, okay? Another name for this is called the Neper frequency. So this is called the natural frequency, and this is called the Neper, N-E-P-E-R, Neper frequency, okay? That's that term right there. So let's go back to what could happen, because it's inside the determinant that's going to matter, okay? Now, there are 3 scenarios where this is bigger than this is bigger than that, or this and this are equal to each other. In the first case, we have both real and distinct numbers. So if alpha, let me just write it over here. If alpha squared, well, we don't need that anymore. We can just look at this. So we're looking at this term right here. If alpha squared is greater than the natural frequency, so if the damping factor is greater than the natural frequency, when you plug in this number here minus that number, you're going to get a positive value because this is bigger. So if that happens, what you get is two real numbers, 2 real and distinct numbers, or values is what I should say. So 2 real and distinct. Distinct means that they're going to be different because one is plus and the other one's going to be minus, okay? So they're distinct and they're going to be real because when you take the square root of a positive number, you get a real number, okay? So if that happens, you get what's called overdamped. Overdamped. Now, what's really cool about overdamped, underdamped, and all that stuff is if you paid attention to the lesson from Friday, it works very analogous to springs. So springs can be overdamped, underdamped, and critically damped. And I'll just quickly give you what they mean from springs' point of view, and then we'll graph what overdamped, underdamped, and all that means. So the way I think about damped and overdamped and critically damped is I think of like race cars or cars in general. They have what's called a shock absorber, which is just a spring. And so when you have no damping at all and you hit something when you're driving a car and you hit like a bump or something and there's no damping, you'll just go up and down, up and down, up and down, whatever. Let's say there was a spring there that no damping involved. Now, if your springs are overdamped, what'll happen is when you hit the bump, it'll go blank and then slowly bring you up again. And so you would want something like this in a race car where you're going really fast. You don't want to oscillate up and down as you're going forward. But the problem is in overdamp, you hit the floor hard. You feel it. So every bump that you go through, if it's overdamped, you're going to feel it. Then you have underdamped. And underdamped is when you hit a bump and then you go up and down a little bit and then you kind of level off as you're moving forward in the car. Now, you would want something like that if you're like living in a rocky place and you have a car like a truck. Trucks usually are underdamped. They have a little spring to them because you don't want to feel all the bumps on the road. So what will happen is every time you hit a bump, you'll oscillate a little bit and you won't feel all that impulse right away. But the problem is you won't be traveling fast when you do that. And then critically damped, which is like the ideal situation. It's not too much here. It's not too much there. You'll feel a little bit of oscillation and you'll just go forward. Okay. So those are what overdamped, critically damped, and underdamped mean in terms of a spring. We'll get back to what the graphs of these look like later on. But just know that if this is what happens in your solution, and you know what alpha is and you know what A is because you'd be given alpha, did I write it? Oh, right here. Alpha is equal to this term right here. So you'll know what R is and you'll know what C is. You just plug it into here and you figure out what alpha is. And you do the same thing here. So you know what alpha and omega are. And then right away, you could figure out whether this is going to be this situation or the next situation and so on. The solution to the differential equation for an overdamped is going to be written just like we had written right there. V as a function of t is going to equal a1 e to the power s1t plus a2 e to the power s2 times t. Okay, so that's going to be the solution for the overdamped situation. Let's move on and talk about the other two. We don't need that anymore. Now you guys are actually getting a real college lecture here. This is what I would teach my college students. I've never taught LRC circuits to a high school class before. But hey, YOLO. Okay, so in the next situation, let's do this one. What happened? How did I write that? Okay, so alpha squared. What happens if the Neper frequency is less than the natural frequency? So in that situation, how am I writing this? Okay. So in that situation, well, you just plug in to your, I don't know if you see that. There we go. You plug into here, and you'll see that you'll get imaginary numbers. So over here, you get an imaginary number because this value is bigger than this value. And then you get two of them because it's plus or minus. So what we would say is that you get two complex numbers. You get two complex solutions, and they're, here's a word for you, conjugate. Two complex but conjugate numbers. So conjugate just simply means it's the plus or minus of a complex. So that's kind of what we're getting with our determinant. Just a quick example, like if you have A plus BI, that's a complex number. The conjugate of this would be A minus BI, okay? So those are going to be our solutions. We're going to get two complex numbers, and they're conjugates of one another. One is plus, one has a minus to the I to it, all right? Now, what we call this, when this is the case, it's going to be called underdamp. All right, so in this situation, we have the underdamped. And what is our solution going to look like there for an underdamped? It's going to be this. It's a complex number, so we're going to have a complex solution to it. It won't be exactly like the V as a function of t before. We'll actually write it like this. V as a function of t is going to equal B1 e to the power negative alpha t cosine of omega d t plus B2 e to the power minus alpha t sine of omega d times t. So that is our solution if we're complex numbers. And what is omega d? Omega d is the damping frequency. And the damping frequency is the square root of the natural frequency minus the Neper frequency. So that would be the solution for the underdamped situation. Okay? And then lastly, we have the critically damped. And in the critically damped, can I erase one of these? I'm allowed. I've earned it. I'll erase this term right here. So the last one is when the Neper frequency is equal to the natural frequency squared. Okay. So in that situation, we have what is called, well, what do we have here? So if these two are equal, then we would say that S1 and S2 are real. They're real numbers because it's 0. The square root of 0 is 0. And they're equal. Okay? So if you do plus 0 or minus 0, it doesn't matter. You get the same value for your solutions. So if that's the situation here, we get what is called a critically damped solution. And for the solution to the critically damped, it's going to be V as a function of t. Our solution for this situation is going to be, well, we used A, we used B. We could use C, but do I use C for something else? I forget. I'll use D. You could use C if you want to. D1 t to the power e minus alpha t plus d2, that's d2, e to the power negative alpha t. And be careful, there's no t for the second. So you're decreasing the polynomial as you go forward. And that's going to be the solution for this determinant right here, if this were our determinant. Oh boy. I wish we could say, okay, that's everything, but there's a little bit more here that we still need to do. The first thing is we don't know our coefficients. We don't know what D1 is or D2 is. We don't know what A1, A2 is or B1, B2 is. So how do we solve for those? How do we solve for the coefficients? What you're going to use is what's called your boundary conditions. And you're going to apply your boundary conditions to the function, whatever the solution is right here, and also the derivative of that solution as well. So let's take a look. A lot of steps to be had here. All right. So let's look at the overdamped situation, okay? So in the overdamped situation, we had V as a function of t is equal to A1 e to the power S1 t plus A2 e to the power S2 times t. So that was the solution for the overdamped. And we want to know what A1 and A2 are. So how do we do that? We take the boundary condition here. So one of the boundary conditions could be the voltage at 0. So the voltage at time equals 0 will give us A1, and then e to the power 0, it doesn't matter what S1 is, e to the power 0 is 1. So we just get A1 here, plus this part, again, e to the power 0 is 1, so we get A2. So here's one condition. And so what this means is this is going to be our voltage at time equals 0. So in the problem, they would probably give that to you, and you can just solve for it from there. The second, so this is equation 1. The second equation, to get to equation 2, we have to take the derivative of this. So v prime of t, that's going to equal a1 s1 e to the power s1 times t plus a2 s2 e to the power s2 times t. And in here, we can take the initial condition again. So that'll be v prime of 0. And so when you plug in here for 0, again, this term would go to 1, and you get a1 s1 plus a2 s2. So you have two equations. This is equation 2. You have two equations, equation 1 and equation 2, and you have two unknowns, A1, A2, A1, A2, where this and this you will be probably given or something like that on a problem. And if not, you can always find it like using a voltmeter or something. So if you actually made a circuit and then you probed it, you would know, oh, at time equals this, it's going to be this much voltage. And so you could set that much voltage equal to this and then substitute in for your terms here. Where S1 and S2 are given to you. S1, you just plug in into this equation right here. So S1 would equal negative alpha, where alpha is known. So this is a number, this is a number. You just plug it into here, and that'll be S1. And S2 would be the minus version of that, okay? And so from there, you can solve for A1 and A2, and then you're done. You've solved your differential equation. You kind of wish you went back to air resistance, don't you? But that's the beauty of this. This actually works out really nice. Now, I'm not going to go through the steps for the other two. I'm just going to give you what they are, and then you can do that on your own later. So if we were looking at the overdamped, so for underdamped, for underdamped, our solutions are going to be, this is for underdamped, V naught, when you plug in, I erased it, but when you plug in for that, the sine term will go away because sine of 0 is 0, and we will be left with just B1. And when we take the derivative and set it equal to 0, we will get negative alpha B1 plus the driving frequency times B2. So those are my solutions, or with the boundary conditions in there. And then you can solve for this, plug it into here, and then solve for B2, okay? And then for the critically damped, solution, we would get V at 0 is going to equal D2, and V prime at 0 is going to equal D1 squared minus alpha times D2. Okay, so just plug in 0 into here, and you'll get the first term, and then take the derivative of this and plug in 0, and that'll be the second term. And that's how you solve your differential equations. This is RLC circuits actually solved. On Friday, I said, there's a lot of math. Don't worry about it. Well, here's the math that goes with it. So let's take a look at what the graphs of these damping things look like. So for the overdamped, the graph of an overdamp will look something like this. You got your term here, your general solution term. And this term right here is given by A e to the power my st. Is it st? I wrote st or minus alpha t? Minus alpha t. So that's going to be my term right there. And then for the underdamped situation, your graph is going to look like, what color could I use? I'll use something like this. The actual solution would look something like this. It would go up, and then it would die down. But it would never pass this line right here. Hence why it's called an overdamp. That wouldn't make any sense. No. It's called an overdamp because it flattens out quickly. It doesn't do the oscillation that you're used to seeing. So even before it can like spring back up, it just decays downwards. And that's it for the overdamp situation. Now the underdamp situation, let's take a look at that. For an underdamp situation, you actually will get a oscillation, but it's going to decay downwards. So it'll do its little bouncy motion and then come down and then go like that and then do that and then that and then that. And you can see that the bounce is getting less and less and less, sort of like a spring. If you put it on a mass on a spring and you let it go, it does this, but eventually it decays downwards. And that's what the underdamped situation would look like. And then the last one is the critically damped. And for a critically damped, your graph would look something like this. It would actually go above the line. It would go above the line. And then as it decays downwards, it would do the same thing as the dotted line, but close to it. So it would decay down just like that. And this is critically damped here. Now, the point where it overcomes our dotted asymptotic line, whatever you want to call it, this point right here is going to be given by the value of 1 over alpha. Okay? So that is RLC circuits in parallel. Let's quickly, if you're coming in now or you came in a little bit later, let's do the series circuit, and everything that I talked about just right now will work similar. There's a few things that are off, but it's going to be exactly the same at the end. Most of it. Okay, so let's look at our series circuit. In our series circuit, what we're going to have is a capacitor. We're going to have a resistor R. And then we're going to have our inductor. There we go. And so here, which way do we want to call it? This is the voltage of the capacitor, where this is the capacitor here. We have our resistor here, and we have our inductor here, L. So the RLC circuit, but it's in parallel, and the current going through the resistor is going in this direction here, I. Okay? So just like we did before, we have to write an equation out with this graph right here. Now for this one, we're going to use Kirchhoff's voltage loop rule. In the parallel circuit, this one right here that we did, we had started with Kirchhoff's current loops or current rule. For this situation, for a series circuit, we're going to use Kirchhoff's voltage loops equation. Whew. So let's write that out. We've got the voltage of the resistor plus the voltage of the inductor plus the voltage of the capacitor, and that's going to equal 0. Okay, so this, and that. Well, that's not a differential equation. We have to write it as a diffeq. The voltage of the capacitor I could write in terms of current. So what is current when we're talking about resistors? It's just I times R. So it'll be I times R. Now, what about the voltage of the inductor? Well, that was, we already had solved for that a while ago. It's L d squared t, d squared I. No, not the second derivative. It's the second derivative of charge. Well, let's write it in terms of I, so it'll be di over dt. There we go. And then lastly, we have the voltage of a capacitor, which I had shown you before. We could write it like this. The voltage of a capacitor I could write like this. 1 over C, the integral of I times dt. That is the voltage of the capacitor. And that's equal to 0. And really quickly, let's just work it out because maybe you forgot where I got this from. We have capacitance or charge Q is equal to C times delta V. And then we multiply both sides by delta T. And then from here, we can solve for the voltage of the capacitor. And that's going to be, how are we going to write that? Well, this term right here is equal to I. There we go. Q over T is just I. And then what we can do is multiply both sides by delta T and divide by C. So I'm going to divide C to this side. We get 1 over C times I. And over here, you're left with delta V over delta T. And then you just multiply both sides by delta T. There we go. And then if you want this to be actually written as a derivative, you would change the delta signs to T signs. So we get V or dV is equal to 1 over C I times dt. And then you integrate both sides, and that's what you get. Okay? So that's where that term comes from if you didn't know. Well, just like I did before in the parallel circuit, I am going to multiply this side and this side by d over dt. And the reason why I'm going to do that is because I want to get rid of that integral sign. I don't want integrals. I don't like integrals. So if I multiply dt over here, this term right here will become r di over dt. When I multiply di dt into here, it's going to become L di squared over dt squared, or d squared I over dt squared. And then finally, what's going to happen here is the integral of dt will cancel out, and you're left with I over c, and that equals 0. And then the last thing to do is just rewrite this so that there's no coefficient on the leading derivative or the highest derivative order. And so that will become d squared I over dt squared is going to be plus r divided by L di over dt plus this term right here. And we're going to write that as 1 over L times C I. And all of that equals 0. And once again, we have our second order differential equation. All right. And so for the parallel circuit, we're going to get the same characteristic equation. We're going to start with just our guess, but this time, hold on. We're going to do it in terms of I's instead of voltages. Look at that. When we do parallel circuits, when we did the parallel circuit, we started with current and we got derivatives of voltage. When we're doing series circuits, we start off with the voltages and we get derivatives of the current. So now our solution is going to look exactly the same. We're going to make our guess. I as a function of t is going to equal a e to the power st. And then we take the second derivative and the first derivative of this and plug it back into here, just like we did before. Might as well, why not? Today's Monday, everybody loves Monday. Monday is the same as fun day, right? Fun day, Monday. and we get AS squared e to the power ST. And then we plug it back into here, and we will get our, you don't think Monday is a fun day? So we will get our characteristic equation, and it's going to be S squared plus, now this is going to be different than the other one. It's going to be R divided by L times S plus 1 over LC, and that'll equal 0. So plug these values into here, and then this is what you should end up with. Finally, the last thing to do is to solve for S using the quadratic equation, and we will get that we're going to get two solutions just like we did before. So I'm going to write this as S1, 2. So solution 1 and 2 is equal to negative R divided by 2L plus or minus the square root of R divided by 2L. R divided by 2L. Well, that's not an R. Come on, man. You can do better than that. R divided by 2L squared plus 1 divided by LC. This is almost similar to the parallel case, but a few things are different. And so 1 over LC is still our natural frequency. That didn't change. Look at that. Because the natural frequency doesn't depend on the resistance, so it shouldn't change. It doesn't matter what you do. The natural frequency is just between an inductor and a capacitor. So we end up with the natural frequency omega naught equaling 1 over the square root of LC. But where it differs is in the Neper frequency, or the damping factor. And the damping factor is going to equal R divided by 2 times L. Okay? And then just like before, we could write it as S, comma 1, 2 is going to equal negative alpha plus or minus the square root of alpha squared minus omega naught squared. And so we get the same result as we did before, and it works exactly the same as I mentioned earlier. So if alpha squared is greater than omega naught squared, you will get overdamped. If alpha squared is less than omega naught squared, you get underdamp. And if alpha squared is equal to omega naught squared, you get critically damped. And I'm not going to do the rest of this, but then you can, get your 3 solutions. So you'll still get one solution that's going to have two solutions to it, or 2 values, and they're both going to be real. The other one's going to be 2 values, both going to be imaginary, and the third one's going to be both real but identical solutions. And that is the RLC circuit in a nutshell. I thank you for joining. Tomorrow we'll start doing some other things with AC circuits. But there is the LC circuit here. Oh, I'm not done. I'm not done. I'm not done. Hold on. I'm not done. I'm wrong. That was a lot of math. Zoe, we're not finished yet. And here you thought we'd be done. Last thing, I promise you, I'm not going to do too much math. I will not. I only a little. I'm not going to do any more math. I'll just give you the solution to it. But at least I want you to be exposed to it, so that you see it. So, what if we include a power supply? Let's say a battery, where you have plus minus here. And we do the parallel circuit first. So the parallel circuit was a capacitor, an inductor, and a resistor. Okay, that's not an inductor. That is an inductor. There we go. We have the C, the L, and the R here. And then we also have a power supply. So what would the differential equation for this look like here? For a situation like this, the differential equation is going to be written as d squared I of the inductor dt squared plus 1 over RC d I of the inductor dt plus I of the inductor over LC is equal to this additional voltage term here, which will be given by I divided by LC. So it's similar. It is similar to what we had done with the parallel without this, but we cannot set it equal to 0. And the other thing is we're looking at the voltage, the current of the inductor, not the overall current. So in this situation, it's going to be very similar to the parallel circuit without the battery, but you don't set it equal to 0. And by not setting it equal to 0, solving this differential equation is real hard. We're not doing that. That's AP Physics E. So we're still in the young phase. We're in AP Physics D. And in the other one, I'll just write it out, if you don't mind stepping just one more second. And there was a switch here too, by the way. So the other situation would be you have your capacitor, you've got your resistor, you've got your inductor, you've got your switch, and then you've got your power supply plus minus some battery here. And the differential equation for that is going to be dV of the capacitor now squared, dt squared, plus R over L, dVc over dt, plus Vc over LC, yeah. And that's equal to V over LC. That's right. So that's the differential equation to that. If you solve for this and you wanted to know what the voltage of the function of time is, the voltage as a function of time will be given by something like this. Vc as a function of t will be given by the final voltage across the capacitor plus whatever this term we call the natural response. And for the parallel circuit, it would just be the current of the inductor for the parallel case. It was the current of the inductor as a function of time is going to be given by the current final plus the natural response. Okay? Tomorrow, we're going to get rid of this right here, and we're going to start dealing with alternating currents. We'll do an easy lesson tomorrow. I'm just going to give you formulas and stuff like that. And then on Wednesday, we will actually do the math and where I come up with those formulas, okay? So I think that is more than enough for today.